Before we get started on this goal, I would like you to stop the video and take this little quiz just as review. Okay, we're back. Let's go ahead and go through the answers. So number one, which of the following are ions? An ion is an atom with a charge. And so we have here positive and negative charges, and all of those would be ions. So the only thing that is not an ion is this one, but it's all of them except for that one. Number two, what is a cation? A cation is a positive ion. And how I remember this is in the word cation, there's a T, and so it's like a little plus sign. So the ones that are cations are A and B. Those are the positive ions. Number three, what is an anion? An anion is a negative ion, and there's two of those. So C and E. And again, there are negative ions, and I remember that because in the word anion, there's two N's. So that stands for negative. And number four, a cation is an atom that has gained electrons. This is false. When you have a cation, that means it has lost electrons. So that's why it's more positive. So it was neutral, but negative electrons left, and so those protons are still there, and so it ends up with a positive charge. In this whole unit, we're talking about bonding, and in bonding, why do atoms bond? They bond because they become more stable. And besides becoming more stable, they also are lower in energy. So the noble gases, they are stable by themselves, so that's why the noble gases do not bond. Remember, they used to be called the inert gases, meaning that they didn't react with anything. All the other elements, they need to bond with another atom and have either sharing electrons or an exchange of electrons to become more stable. How it bonds determines its properties. And so we're going to be talking about that later on in the unit. All right, a lot of times we say things like, oh, that atom wants to gain an electron, or that atom wants to lose an electron. That is not what's happening. Instead, we should say just a little tiny bit of energy given to sodium and it can lose electrons. We can also say that if you give a lot of energy to fluorine, then it can lose electrons also. But as far as between which element will lose or gain electrons, having a low amount of energy to lose an electron, that is more likely to happen than it would for fluorine. So fluorine, chances are this is not going to happen because it just takes too much energy to do that. And so we find that metals, it takes a little bit of energy to lose an electron, but nonmetals, it's so large that that's just not going to happen. All right, first ionization energy. So ionization means we're making an ion. And remember, an ion is an atom with a charge. So that's what ionization energy means. And if I look at first ionization energy, that means it's the energy required to remove one electron, the most loosely held electron from the element. And most of the time, this happens with metals. So metals have a very low amount of ionization energy. Nonmetals have a high amount of ionization energy. So again, low over here with metals and high over here with our nonmetals. So this is the trend. As I go towards those nonmetals, this is an increasing in the ionization energy, and as I go up, there's an increasing in ionization energy. The higher the ionization energy, the higher the attraction between the electron and the nucleus. And if you recall, we have talked about the size of atoms, and the smallest atom that we have is helium. So very, very small atoms here, and the largest atom that we have is francium. And so if you notice, the trend of smallness follows the first ionization energy. And that's because the smaller the atom, then the closer all the electrons in that small atom are to the nucleus. And so then to go and rip it apart from the nucleus, it's going to take more energy. And that's what we're looking at with ionization energy. So again, nonmetals have very high ionization energy, or that is the energy to remove an electron, and metals have a very low ionization energy. All right, this is a graph that uses the height of the column to show the amount of ionization energy. And let's just go through and look at each row. So the very first row, that is the row with hydrogen and helium. And we see that hydrogen is lower and helium is higher. So your noble gases, they have very high ionization energy. Again, ionization energy, the energy of removing one electron. So all your noble gases should be really, really high. So that trend holds there. Let's look at the next row. So looking at the next row, we see that lithium is lower than beryllium. And then when we come to boron, we would expect it to be lower, but there is something going on here that for some reason there's this little glitch. So boron is actually lower than beryllium. Why is this? And this is because there is a difference between removing an s electron or a p electron. So let's look at beryllium. So beryllium, when we look at its orbital, has a 2s orbital, and there's 2 electrons in it. And then let's look at boron. So boron, it has a 2s orbital, just like beryllium, but it also has a 2p sublevel with 3 orbitals. And in the first orbital, we have 1 electron. When I'm looking at ionization energy, I am looking at the difference between removing this electron and removing this electron. So the difference between an s electron and a p electron. And what we find is for s electrons, their electron clouds penetrate closer to the nuclear region. So in other words, an s electron tends to be closer to the nucleus than a p electron does. And so because of that, it's harder to remove. So again, s electrons are harder to remove because they're closer to the nucleus. Okay, so that's the little blip that we have between beryllium and boron. The beryllium is just happens to be higher because we're removing an s electron, and boron is lower because we're removing a p electron, and p electrons are a little bit easier to remove. Let's go ahead and keep going across that second row there. So we have boron is lower than carbon, and carbon is lower than nitrogen, so that's following in our trend. But look, here's another little glitch here in our trend of left to right increasing in ionization energy. We see that oxygen is just a little bit lower. I kind of covered it up there. Oxygen is just a little bit lower than our nitrogen. So let's take a look at that. So again, I'm going to use the orbital diagrams, and let me just clear this a little bit so that we can see. So we are going to look at nitrogen and nitrogen's p electrons. So when we look at its p electrons, we have one electron in each orbital of that p sublevel. And then oxygen, also we can draw the 2p, and we can draw in those electrons. So oxygen has 4 p electrons. And so what we're looking at is we're looking at removing this electron and also this one right here. So what's going on here? So in nitrogen, we have 3 p electrons. They each have their own orbital. And so when we go to remove the most loosely held electron, it's just that electron in that last orbital. Now look at oxygen. Oxygen, its most loosely held electron, is sharing an orbital. And so there's 2 electrons in that orbital. And what happens when you have 2 electrons together, they're the same charge, they're going to repel each other. So to go in and rip that electron away, because of that electron repulsion force there, it's actually easier to remove this electron. So it's easier to remove an electron that is shared in an orbital. So it's not that the nitrogen is so high to remove that electron, but it's just oxygen is so low. So that's why it dips down like that. So as you continue across the period, you do see that fluorine is higher than oxygen, and neon, being the noble gas in that row, is the highest of them all. So our trend mostly holds up. Of course, looking at it as a metal, non-metal, non-metals will always be higher than metals. That's another way to remember it too. All right, one more thing to talk about. When we look at a periodic table, we find that down here at the bottom with the large atoms, that we find that they have a low ionization energy. You would still have the nonmetals be higher in this area than the metals over in here. But in the family, the large atoms at the bottom would be lower ionization energy. And this has to do with the size of the atom. So when you look at an atom, nucleus in the middle, and they have all these energy levels. And as the atom gets larger and larger, the electrons on the valence electrons, the very outer electrons, they are loosely held. And we find that the electrons that are inner electrons are going to shield the nucleus's pull of those outer electrons. So this is called shielding effect. So again, it's these core electrons that are going to shield the pull of the nucleus on those valence electrons. And so this shielding effect, this causes it to be easier to pull off that last electron. So again, shielding effect means that that it's easier to remove an electron. So all your large atoms, it will be easier to remove that most loosely held electron versus your smaller atoms. All right, so what we've been talking about to get fancy is Coulomb's law. So Coulomb's law just means that electrons repel other electrons. So we've talked about that. If they're in the same orbital, there's some repulsion forces that go on there. Also, we have electrons being attracted to the protons in the nucleus. So, or opposite charges attract. And distance is important. So if you have a core electron, so it's close to the nucleus, it's going to be held tightly by that nucleus and so therefore be harder to remove. If you have an electron that's further out, so a higher energy level like with those large atoms, it's going to have not as strong attractive forces because of distance. So this is what Coulomb's law says. So again, like charges repel, opposite charges attract, and distance is important. The closer you are, those like charges will hold on tighter to each other. All right, let's tie this into activation energy, which we've talked about before. So when we look at a potential energy diagram and we look at our activation energy, so remember the activation energy is the energy required to start a reaction and to make that activated complex at the top of the energy hill. And so I'm just going to draw two potential energy diagrams with different activation energies. This one has a very low activation energy, and this one has a very high activation energy. So let's look at it as far as the ionization energy, or the energy required to rip off an electron and create an ion. So if I have a low activation energy, I also would have a low ionization energy because it doesn't take as much energy to remove that electron. So very low activation energy, so therefore low ionization energy. And if I have a high activation energy, I would also have a high ionization energy. So between these two diagrams, which one do you think metals falls under? Do metals have high or low ionization energy? And we find that this first diagram more represents metals. So low activation energy and a low ionization energy. This one right here represents our nonmetals. So chances of a nonmetal losing an electron are very low just because the ionization energy and also the activation energy is so high. All right, so look at this and see if you can answer the questions 1, 2, 3. Go ahead and stop the video and see if you can figure it out. Be careful what I ask you. Sometimes I ask you higher, sometimes I ask you lower. In this case, I'm asking lower, so make sure you understand that trend. So stop the tape and answer it. Okay, we're back. So looking at the periodic table, we find that the lower first ionization energies are going to be closer to where the metals are. So more on the left-hand side of the periodic table or on the bottom of the periodic table. So we have calcium and magnesium, and calcium is lower than magnesium, so this would have the lower first ionization energy. Looking at number 2, we have iron and zinc. We have iron is closer to the left-hand side, or where the low ionization energy is. So that is the low one. And then on number 3, we have neon and fluorine. So they're next to each other on that second row. They're both nonmetals, but we find that neon is a noble gas. So it should have the highest ionization energy of that row. And here we want the lower. So it's going to be fluorine.